Good morning, good evening, good afternoon to all of you. So my name is Pascal Vivet from CEA in Grenoble, France. So it's my pleasure to chair this last day of the presentation for the 3DIC conference on Thursday. So we have this morning a presentation about heterogeneous integration and design aspects with 3 invited talks. So the first talk is dealing with heterogeneous integration. It will be given by Alan Huffman. So Alan, I suppose you are here as well?
Yes.
Yes. Hi, Alan. So let me present you shortly. So Alan is Director of Engineering for Micross, a company that provides advanced interconnect and packaging services with primary focus on the US military and aero market. His role is responsible for technology development and implementation strategy, strategic business development, and program management for all of Micro's advanced interconnect and integration technologies, including wafer-level packaging, heterogeneous integration, and advanced interconnects. For over 25 years, his work has focused on the development and implementation of advanced interconnect technologies, including fine pitch bump interconnects, silicon interposer and heterogeneous integration, characterization in wafer-level packaging, and infrared and optical device packaging. He has authored and co-authored numerous papers and presentations on these topics. Alan is a senior member of the IEEE Electronic Packaging Society and serves as the EPS VP of membership. So, Alan, the stage is yours.
Thank you, Pascal. So, as Pascal said, my name is Alan Huffman. I'm the Director of Engineering for the Micross Advanced Interconnect Technology Group that's located here in Research Triangle Park. And the talk I wanted to give today with the time I have is it's entitled "The Devil is in the Details." And it's a collection, if you will, of viewpoints and considerations that we've collected in numerous engagements with our customers, both in the aerospace and defense and in the commercial industry, about all of the different things that go into planning a heterogeneous integration system. And most notably, some of the things that people leave as afterthoughts that they don't think about early in the planning process that end up being things that they have to solve later on and somehow create solutions that they might not otherwise have had to do if they had given adequate consideration to all of these different details up front. So this first slide is no surprise. We're going to move quickly through that. There's a lot of adoption of heterogeneous integration technology today. A lot of companies that are looking to get involved in this. It's been a fairly high volume engagement now for first tier vertically integrated foundries and OSAT. So, some of the example companies that you've seen here who have products in the marketplace now are listed. And over the course of that time, as you can expect, there's been a delayed adoption of these technologies and a lot of development that's going on in the aerospace and defense and U.S. government supported program space over the last several years. We've been involved in a number of those over time. The VISA sensor array, the DAHI program, the CHIPS program are some examples of those things. There's current programs now in the United States, most notably the SHIP program that's driving this. As an example of a timeline of some of those programs over a few years, you can see the timeline of these programs. I'll call out the VISA program that you see there in the 2000 space. That's one that we were involved in, where we were developing heterogeneously integrated 3D chip stacks. And later on in the CHIPS program, we were supporting that as well. So there's a lot of activity outside of the high volume environment, and where you don't have vertically integrated companies who are driving all of these design and assembly and fabrication solutions, it's helpful to start looking at these considerations for companies that are just entering this space or maybe new to this space or maybe fabless or have design ideas, and how do they now take those ideas and work with external providers to help support their microsystem fabrications. There are a lot of things that you have to touch on here. This list is by no means comprehensive, but it represents a lot of the topics that I'm going to touch on today here with the design considerations, particularly if you're going to be looking at some sort of heterogeneously integrated silicon interposer approach. The availability of functional devices and all of the physical interconnect options and requirements that you're going to have for those. What about fabrication of advanced substrates and in particular passive or active silicon interposers that are going to serve as that integration platform? There are a number of assembly process considerations that get driven by the components and their ability to be interconnected to one another. And then of course, at the end, there are going to be test considerations. You might only really be looking at the electrical side of things early on, but eventually things like reliability are going to be important. So our experience is that a systematic approach to considering all of these elements is very important to do early on in the design phase while you're determining components and methodologies and paths that you can follow for your microsystem, and looking at how you can avoid problems downstream is very helpful. These archetypal heterogeneous integration modules are fairly well known. On the left, you have the typical 2.5D HI module where you have a silicon or glass interposer with TSVs, multiple devices that are integrated on the top side, bottom side that's been connected to most likely some sort of organic substrate. And on the right side, you have the 3D HI approach, chip stacks, through silicon vias required in functional layers here. All of that now sitting on top of some sort of substrate. Maybe it's an interposer, maybe it's an organic substrate. This is pretty well known, but I also wanted to use that as a prelude into some examples of how those technologies are realized at Micross today and some of the things that we offer and support. So you have the wafer level packaging side of this thing that supports the off-chip interconnect, the mechanical and electrical connections between the components. You have the silicon interposer capability, which requires the through silicon via fabrication. Those through silicon vias can also be implemented into finished CMOS devices as long as they're designed for a post CMOS TSV insertion. So the 3D IC picture in the top right is an example of that. You're going to need the capability to do multi-layer routing processes. Is that going to be done with multiple layers? Maybe you only need a few. And as you begin to start looking at very high density components that are being interconnected, densities even beyond current high volume copper pillar bumping today, there are solutions for being able to do bump interconnect pitches at 10 microns and even beyond to allow for mechanical and electrical interconnect of the components. We'll start with design considerations. The obvious questions of what's the microsystem going to do and what devices are going to be required and what the performance metrics are things that system designers generally start with. And we like to give some thought to a number of downstream considerations at this point. Most microsystem designers are going to be deciding very early on what devices they want to interconnect. But the question of the availability of those devices and what sort of physical interconnects are going to be available on them turns out to be a really big question. So devices can be identified from a manufacturer's list of offerings, but will those devices need to have bumps applied to them? Are they only available in single die format? Are they going to be available in wafer level formats if you need to do bump interconnect or any sort of other interconnect processing prior to integration? Are you going to need to put TSVs in them? If you are, is that going to be an offering from the foundry? Is that going to have to be something that you apply after the fact? And assuming that you're going to have an interposer necessary, what sort of requirements for the routing layers and for the TSV interconnections are going to be needed? These are all considerations that you need to be thinking about from a design perspective very early on that all have to do with how these different elements are going to be interconnected and fabricated. On the device availability side of things, as I mentioned, understanding whether your devices are going to be available as individual chips with reasonable lead times. Are those individual devices going to be provided in bumped states that are ready to assemble? If they're not going to be available in that form, what are your options? Do you have the ability to procure full wafers from the vendors? Obviously, we see a lot of issues with time delays if you're going to be ordering wafers from providers these days. If you've got individual devices that are available, what are your options for interconnect there? the things to keep in mind is that you're usually going to be thinking about a bump device when you're doing a heterogeneous integration. Solder bump array C4s or copper pillar bumps are typical for a lot of the 2.5D solutions that are employed today, even 3D solutions. And if you only have full device wafers, then you can perform those bump interconnect processes very straightforwardly. But you can see cost and lead times varying greatly. You can see the availability of different devices varying a lot. And so having the ability to consider different options for similar devices that may perform the same function may need to be something that you identify very early on, because if you exercise all of your design around a component that's not available or is just not capable of being processed in a way that it can be integrated, you end up having to rethink a lot of your design. On the side of dealing with individual devices, there are pathways to be able to do bump interconnect for individual devices. There are providers who will do die level electroless UBM deposition or solder jet kind of operations to provide a component that can now be bump interconnected like a flip chip. But that same approach may not be very feasible to do if you need a high density interconnect like a copper pillar. If the full wafers are available, obviously, then you can take advantage of state-of-the-art bump interconnect capabilities. I've listed a few of the options that Micross offers today that run everything from WLCSP all the way down to fine pitch copper pillar. So those are relatively simple solutions to employ as long as wafer level components are available from your vendors. We look at the silicon interposer now. Procurement of silicon interposers globally is still a question. If you're top tier customer and you're working directly with first tier foundries and OSATs, interposers are available, but there is a real question still about companies who want to do low volume or looking to do prototyping and development kind of work. Where's the availability of lower volumes of interposers? Those options are much more limited. They require sometimes managing multiple providers to do the fabrication. So you may be looking at a design partner, a back-end foundry, a TSV insertion process, an interconnect structure process, and singulation processes. And so having a single point of contact who can provide a turnkey service for those sorts of operations and coordinate a multiple group of providers is an advantageous thing to take advantage of. And so that's one of the things that we've been working on, is to develop an ecosystem of sorts to provide silicon interposer support that includes the design side of things, taking the microsystem design and designing into foundry processes so those devices can be manufactured, whether that's back end of line routing, for example, or other sorts of routing processes, the through silicon via processing, which we support internally, interconnect structures, which we support internally, and then singulation and handling, which we can support internally. There's a couple of examples here. I'll show on the left side, passive test interposer device that we fabricated with TSVs, fully passive, a couple of routing layers that have been done internally that could be extended into doing multiple routing layers with a back end of line foundry partner, and then doing TSV insertions after the fact. That's an example on the right where we've done some TSV insertions into a CMOS device after the fabrication has been completed. So the CMOS has been designed to allow TSV insertion after the completion of the process from the front side of the wafer. And then building up interconnects and doing the assembly of those components together. Our typical TSV dimensions for interposer applications tend to be in the range of about 150 microns in depth. And that's somewhat advantageous because what that means is you end up with a substrate with sufficient thickness that it can be handled relatively safely and relatively easily with standard assembly tools. But you may find that if you're getting this component from a foundry partner, that you're going to be looking at thinner thicknesses of silicon. Typical device foundry processes are in the order of 50 micron deep for the TSV. So functional devices with TSVs can often be on the order of 50 microns thick. If you're looking at a partner who might be doing a passive interposer in a foundry process, you might be seeing depths on the order of 100 microns or so. So that's a consideration to take into account from the assembly perspective. You need to have a relationship with somebody who's very well versed in foundry process design kits, who can take your design and translate that into a process that a foundry partner can support if you're looking for multi-layer metal routing capabilities. That routing design is going to need to incorporate keep out zones if you're going to be doing TSVs in that structure at the end of the front side routing. And the TSV dimensions need to be considered as well. As an interesting note, the emergence of glass now as an interposer has been around for some time. There's been a lot of efforts and a lot of work that's been done in trying to look at how to utilize glass in interposer operations. It has some very advantageous material properties, obviously, for high frequency applications. And there are providers now who are able to build those substrates in such a way that it's pretty simple now to utilize through silicon via processes to put the similar structures into glass. But if you're looking at doing very high level multi-layer metal routing, the options for being able to do something that would be similar to a back end of line multi-layer routing process, those are much more restricted than they would be for silicon. The assembly considerations. Obviously, you're going to want to have a high accuracy bonder or assembly system that you can utilize devices that are going to have high IO densities. 55 micron and smaller copper pillar arrays are not uncommon for these devices. And you certainly have the chance of having multiple components that have different types of bump interconnects. So you may be combining C4 solder bumps with copper pillar bumps, depending on what your devices are. You may even be looking at gold thermocompression bonding. So having a very flexible system that has a wide array of assembly process capabilities is good to have. Handling of thin devices is challenging, obviously. A tool that has all of the capabilities to safely handle those thin devices, as well as how those are going to be moved from singulation processes into assembly processes, particularly if there's going to be shipping involved. Depending on where the bump interconnects are going to be on the various components, there's a real big need to determine the order of assembly for those components so that you can develop a process that's going to have the best yield and most efficient process flow. And then you're going to be looking most likely at underfilling these components, at least in some point in the future when reliability becomes more of a factor. And that may require new materials or non-standard deposition methods where you have very large components, or you have very small chip substrate gaps, or you have very high bump densities where the challenges for underfill dispersion are a lot greater. As some examples, the preferable flow that we like for assembly of these systems is a bottom-up approach where we can begin with a substrate, most likely an organic. We can attach the interposer to that relatively standard kind of bump interconnect process, underfill that for stability, and then put the multiplicity of the devices that are going to be bonded to the interposer on last. And so that provides you with a stable structure to be able to build everything up. But of course, it means that all of your bumped devices have to be available with bumps. And it means that you're going to be fabricating your interposer with the bumps on the bottom. And on the top side of the substrate, on the top side of the interposer, you're going to need solder compatible bond pads. All of those are pretty straightforward things to do with standard processes today. If you have devices that you need to support, to put on the interposer, and you don't have the ability to do the bump, or if you have an interposer with bumps on the bottom, that becomes a very difficult substrate to handle. So now you have bumps on a substrate that you really can't fixture in most assembly tools. If you're now trying to assemble devices to the top side of that interposer with bumps on the bottom before you attach it to the substrate, that becomes very difficult to do. So an alternative is that you can simply flip the bump connections to the other side. Perhaps you don't have bump connections at all on your interposer. But if you do that, do you have the opportunity then to put the bump array on your substrate and allow your interposer to be held with a flat backside, do all the device assembly on the front side, and then make the interposer connections to the substrate last. That's not always easy to do. It does present some challenges in the interposer fabrication process as well. And does it put the bonded devices on the front side at risk when you're doing the second level of assembly? How do you handle, for example, that construct with multiple devices on the top side and assemble it to the substrate? Even more difficult is when the chips don't have any sort of bump bonds at all. So now the question of having the devices with some sort of bump compatibility metallurgy is needed. And the prospect of putting bumps on both sides of an interposer is a much more challenging process flow because of the fact that you're using temporary bond processes to process the thin wafer. This requires now multiple transfers of the wafer to bump both sides. The difficulty in removing a bumped array side from a temporarily bonded carrier is certainly there. So there are thermal issues, there are mechanical issues that come into play. And that introduced a lot of risk into the assembly process if you don't have the ability to drive bumps into the component side. And finally, if you're looking at the test considerations, we're thinking about testing this completed module. Wafer level testing of the devices is obviously preferable. You don't want to be putting devices that are not known good into these modules. The rework of those devices can be very difficult. So are you going to do known good die testing at the wafer level prior to singulation? If you are just getting devices from the vendor, are they also known good? If you're doing interposer testing and you need to know the yield of the interposers, a couple of things that you might want to consider are, do you incorporate a TSV test vehicle of some sort? Do you have the test chain, for example, that provides you TSV yield and resistance data that you can measure? You also have, if you're looking at a complicated interposer with front side routing, the need to perhaps do some sort of testing of the routing metal layer so that you know going into your assembly process that you have a known good interposer. How is that going to be accommodated for? You're going to want to do that at the wafer level if at all possible as well. The final assembled module testing usually requires the development of some sort of customized test architecture, socket or interface of some sort, all the test protocols and programs. That is an extremely long cycle to develop all of that hardware and test protocol for a very complicated microsystem. And then eventually you're going to want to know whether or not this thing is going to live in the field for the application it's intended for. So thinking about all of these assembly processes and interconnect structures in terms of how they're going to hold up in thermal cycling and high temperature storage and HAST and THB and shock and vibration testing downstream is important. And depending on what the operating environment is going to be for that module, you may just be looking at doing the functionality testing alone in the early stages of your program. So in summary, there are a lot of details that you have to consider when you're building a heterogeneously integrated package. Many of these choices that get made for one component impact what has to be done to other components. And so you can create a domino effect of problems that you have to solve downstream if you don't have the flexibility or the forethought to avoid those problems up front. Having functional devices in a bumped format leads to the most straightforward approach. This is a question that we work with our customers with on a regular basis. It's very common for us to get a list of devices that they want to work with and then find out later that they're either not available in a bumped format or they're only available in bare die format, and then really having to backpedal and find other options that might be able to perform the same function. Successful interposer fabrication requires all the routing layer requirements, the foundry process capabilities, and the TSV fabrication processes are all considered together, because you're probably going to be looking at, in a lot of cases, utilizing multiple providers to perform those functions. And if you can find one provider who can help coordinate and arrange all of those and help you decipher the options that are going to be the best fit for your application, so much the better. And then the assembly and test solutions have to be given thought early in the planning cycle so that you can avoid downstream incompatibilities that may lead to time-consuming workarounds, if a workaround is even possible at all. So with that, I'll bring my talk to an end. Thank you very much. Any questions, I'll be happy to answer.
Okay, thank you very much, Alan, for your talk. Quite complete. And so any question for Alan in the room or for people online? Please ask your question through the chat if you have any. Any question? Okay, so doing people. Alan, I have a question. So you've been talking about test and stress. So for your application, I suppose that thermal stress and mechanical stress can be quite difficult. So have you studied systematically at design phase the thermomechanical impact in terms of reliability using CAD tools modeling? Have you done such study?
Yeah, good question. So we're working with some design partners who have that modeling capability that they can employ as part of the design phase. So, that's not something that we do internally, the modeling side of this, but it is something that we have created partnerships with companies, particularly on the design support side, that can provide that early thermomechanical modeling input into the design. So if you're looking at, different materials or substrates or component sizes, underfills, bumps, whatever, those can be taken into account early in the design phase before you start fabricating anything, so that you really understand.
Sure. Okay, Alan. And then my other question is, because I suppose that you may use your devices in some severe and harsh environment. Have you observed some reliability issues of your 3D packaged devices due to large size of the interposer or due to any issues of bumping on the field that you had to fix?
We haven't seen any direct problems yet. Now, I will say that a lot of the programs that we're involved in, the engagements that we're working on, are still very much in the feasibility development phase. So the deployment of large scale fabrication of those modules into reliability testing is still in the future. But it's certainly something that's on our mind as we're looking at, the assembly processes and materials and sizes of components.
Okay, thanks. That makes sense. Because many people are talking about reliability issues of all these devices, and it's kind of difficult to have real numbers and real feedbacks of people knowing if there are issues or not, because CAD modeling and CAD correlation is interesting, but are we facing some real issues? And we don't always really know. Okay, thanks for your feedback, Alan.
Absolutely. Thank you.